Oh, hi. How's it going? I hope you got those lines up, got those algorithms working, and that's all well and good. Now, in this session, we are going to get 3D perspective projection working. Now, I can't overstate how much reverence I have for this technique. It's just really cool taking three-dimensional data and drawing it in 2D. It just blows me away every time. So, without further ado, let's get into it. All right, so let's get into the theory. We have some three-dimensional data. How do we put that on the screen? Well, we're jumping the gun a little bit because that's presuming that we have three-dimensional data. Now, let me draw a little diagram. Let's say we have... Sorry, I got to start over. That's not good. Let's say we have a space and we have a camera, and the camera is looking out from the origin in some direction. Okay, let's add a convention here. Let's say that left and right is the x-axis, positive x is to the right, negative x is to the left, and let's say that our y-axis is our vertical, up and down, positive is up, negative is down. Now this is a little different to how our screen works, but we'll correct for that. And then we'll have the z-axis. Now, which z direction is positive? Well, everything needs to be based in mathematical reality. So if we take our fingers and we curl our right-hand fingers from the x to the y, the direction of our thumb, by convention, is the positive z-axis. This is similar to OpenGL. For some reason, a negative depth is always in front of the camera, the thing that you're looking at. That's a little strange, but I'm going to stick with that convention. So let's say we're looking at a box. I'll just put a bunch of points here. This is the front face of the box. Okay. I'm going to label these points. So I'll say this is point 0, 1, 2, 3. And then between those points, we'll have some edges. Those are the things that we draw. Now, at the moment, I've drawn it so that, again, if I curl around with my right-hand fingers and point towards the camera, it's pointing at me. However, in this video, I'm not doing any backface culling, so it's not super critical. It's just important to note, I guess, maybe for later. And then, if we extend this back, we'll have some other points. And those are the other edges of the box. So I'll just, again, not super critical at the moment, but just for reference, I will define these. So then we'll go point 3, not 3, 4, 5, 6, and 7. Okay, so that is more or less the scene that we'll be drawing, but in addition to points, I'm also going to need to define some edges so that I can draw things. So imagine I'll have an edge which goes from point 0 to point 1, point 1 to point 2, 2 to 3, and then 3 back around to 0. These are the edges of what I'll call my front face, and they will be referring, each of these will be an integer referring to a point position. Okay. The way I'm going to store this is I'm going to have a big list of all the A points. And then I'll have a big list of all the B points, and I'll reference into that. Okay, so that's all well and good. We'll also need some back faces. So for the back faces, I'll go 4 to 5, 5 to 6, 6 to 7, and then 7 back around to 4. Okay, so that's my back. And then that's not going to cover everything because I'll still have these little miscellaneous sides. So this is what I was saying about, don't worry too much about backface culling or anything. I'll just add in some arbitrary edges. We'll go from 1 to 4. That's this edge here. From 5 to 0. That's this edge. 3 to 6. And 7 to 2. And now with those 12 edges defined on those 8 points, that is all the data I need to render. Okay. So then the next point is, how do we display things? How do we display things on the screen? So I'm going to go with a matrix operation method. The reason for that is this will be the same method that we would use in a hardware rendering system. So whether we do it by hand or we take that and run it on the GPU, we'll be using the same mathematical structures. There's no gimmicks. No gimmicks. Okay, so what I'll do is I'll start with a point. And by the way, for more information on how to construct projection matrices, I will link a video up above, which I recorded previously, which goes into more details on some of these bits. But the idea is we'll start with a point in world space, and we have X, Y, Z, and then traditionally we keep a 1 in the fourth component of the vector, and that is used to apply translation transformations. Then what we'll do is we'll hit it with a projection matrix, or multiply it with a projection matrix, and that will transform the points a little bit. So the X will get transformed somehow, the Y will get transformed, the Z will get transformed, and then, as it turns out, the depth will be encoded in the fourth component. Then what we'll do is we will perform perspective division. So we take that X point, divide it by the fourth component. So this is performing perspective division. And this gives us, this coordinate is called NDC, and that stands for normalized device coordinates. So the way normalized device coordinates work is that in the X, an X coordinate of 0 has to correspond to the center line of the screen. A Y coordinate of 0 has to correspond with the center line of the screen. Let's set it so that a Y coordinate of 1 corresponds to the top of the screen, a Y coordinate of -1 corresponds to the bottom of the screen, and so on and so forth. So the goal is that I take my point, I transform it with a projection matrix, I divide the components by the fourth bit, which encodes the depth, and then these X, Y, and Z coordinates should be between -1 and +1. Now, I'm not going to worry about it too much if they aren't right now, because clipping the view will be a later video, but that's what I'm working with right now. So the question is, how do we take a normalized device coordinate and translate it into a coordinate that we can put on the screen? Well, my screen coordinate for my X, I'll say, okay, what happens when X equals 0? I want it to be right at the center of the screen, so that's width over 2. Then, for a positive X, I want it to shift to the right, so I'll add the X coordinate of the NDC, but then I'll scale it by half the width. So that makes sure that if I add or subtract half the width, I'll be within the screen. So essentially I'm scaling that -1, +1 up. And then similarly, for my Y screen coordinate, that will be my screen height divided by 2 for, the center of the screen, minus the NDC coordinate times height over 2. And that is to account for the fact that I want to change this positive, I want to change the axis around. So a positive height, I want it to be actually below the center of the screen. If that makes sense, and I may decide to change that later, but right now this makes mathematical sense, so we'll go with that. Anyway, that's enough theory. Let's get into the practice. Okay, so here we are with our project ready to go. Now we are going to need to do a few things. So we're going to need to take the linear algebras files and just copy those over into our project. Open up the project. And here I can see I've got the linear algebras source files. That's awesome. Just right click and go to add existing item. And I'll get both of those files. Just click add. And this might take a bit to get it working. Sometimes I have trouble with this. So what I'll do right now is I'll just put another line down below and I'll include the linear algebras header, and I'll just run that and see if I can get that working right now. Okay, so it says there's some errors. Now, just super quickly, if we get errors and things, we can just go build clean solution. I think this is from a previous build that I did. Okay, so this is fun. Let's do a little debugging on the spot. So what I had is I had a previous build of this project with the source file added in a different folder. And then what I've done is I've gone in here and deleted the folder without removing it in Visual Studio. And it's not liking it. So what we can do is I'll just search here, and I'll search for, here we go, okay. In here, so here we have linearalgebras.c, and then down below we've got this model.cpp. So that's actually the old one. So I can just get rid of that, save that, and just check if I can get that to, please. Yeah, reload all, that's fine. Please work, please. And that's fine. So now we're on to where I was. So it's complaining unresolved external symbol linalg close. So if we go to search for, it says make rotation. So linalg make rotation. Down below, yeah, we have this function linalg close. I think I was partway through making this when I uploaded. It should be linalg close vec3. That's fine. We can just give that another go. Errors, that's fine. Right. Okay. Unknown function min. Yep, that's fine. So we'll just go back again. Okay. So this is line 459, make rotation. That should be f min f. I know, it is what it is. Okay, so fingers crossed, just give that another go. It's important to sort of get this stuff out of the way in the beginning. Yeah, there we have it, that's fine. That is fine, I'm happy with that. So, now, just go down to run. All we're doing right now is clearing the screen. So let's go to the header and add a new function, which I'll call it projection test. And I'll perform that. I'll write the code here. So what I'm doing here is I'm constructing functions with setups and teardowns so that I can simply comment or uncomment and it'll run various modes and demos and things. Anyway, so what I'm going to need is I'm going to need the linear algebras header. If we head into this file, we see that there's a bunch of structs which might be useful for us. In particular, this vec4. Now see, this vec4 has two fields sharing the same data location. That's the vector and the data bits. So this array of floats is used if I want to access or modify individual floats, and this lump of 128 bits is if I want to do a math operation on everything all at once. So I'll make a bunch of those. I'll just go up here. Oh, yep, I'm including that. Okay, that's fine. And let's go. Okay, so I'm going to set up the set of vertices. Now, it's not a lot of fun watching this, so I'll go through it super quickly. Okay, beautiful. So there we have the 8 points that I'm going to use to render. Let's log that out and check that those points are coming in correctly. So we'll go. Okay, so I'm using data to access the individual dimensions x, y, z, and it's often called w, the fourth component, and I'm accessing the ith vertex from this array. Okay, let's give this a go. Don't forget, at the end of the function we need to set logged to true so that we only print this info out once. But yeah, so let's do it. Okay, cool. So beautiful. If we match this print against the initial data, we can see that we are, in fact, declaring those points properly. So then the next point is we need to transform them. So let's go ahead and declare that we will have a second array. Typically what we would do is have an array for the initial vertices and an array for the transformed vertices. Okay. And now let's make a projection matrix. So this is using the mat4 struct from linear algebros. And I'll use the linalg make perspective projection function. Okay, so what we need to take in here is a field of view y in degrees. I just want to keep the same horizontal and vertical aspect, so I'll go with 45 degrees. Then an aspect ratio for the screen, so that is the width over the height. So I'll just go with 640 over 480, that's fine. Then the near distance is 0.1. I don't want anything closer than that to render. And the far distance I'll set at 10. These are pretty standard values. So then what I want to do is I want to loop through and record the transformed vertex. So what I'll do is I'll go for So in order to do this, I want to multiply a vector by a matrix, and I'll go linalg mul mat4 with a vector 4. Okay, and the matrix I'll take in is that projection, and the vector that I'll take in is the ith vertex. Okay, so let's just give this a go and see that this works without any errors. Foreshadowing, there will be errors. Okay, so, I mean, this is one of those things, it's just being a little weird. It's saying, hey, we don't know like what's going on here, we don't get it. So, strange as it is, I know, strange. I'm just going to rename this and call it a CPP file, this linearalgebros.c. Oh well, it was fun while it lasted. So now if we run this, it works with no errors. Okay, so let's have a look at those points. So after applying those transformations, I should have a set of points which are all transformed. So I'll say, let's get the projected things, and I'll read off the ith transformed vertex. Have a look at that. Okay, so have a look here. What we've got, this is really important, the way this projection matrix has transformed the data. It has shifted things around a little bit in the X, Y, and Z, but most critically, it has recorded the depth how far each fragment is away from the viewer, how far each pixel is away from the viewer. So what I need to now do is run through here and divide all of the coordinates by the fourth coordinate. So I'm actually going to apply that perspective division right after projecting. So I'll take the 0th component and divide it. There we go. And then I'll do the same thing on the Y and Z. I could do it on the W as well, but I don't need to, so I won't. There we have it. Now let's give this a go. I've picked this so that all of the coordinates will be within the view space. So they should all be between -1 and +1. Give that a second, and yeah, there we go. Beautiful. Okay, so these are all things that I can plot on the screen. Okay. So now what I want to do is I want to transform these into screen coordinates. So I'll do the same thing as before. So remember what I was saying, half of the screen width, so 640 pixels, half of that is 320. And then the same thing over here, so 240 is half of 480. Okay, and now let's print this out again. So I'll say, alrighty, these are the screen coordinates. Just to make things nice, I'll cast these all to integers before I print them out. Okay, let's give that a go. There we go, close that down. And yeah, nice. Okay, so as you can see, these are all things that we can plot. I think I forgot to put the end bracket there. It doesn't really matter, but there we have it. Okay, excellent. So let's get in and plot these on the screen. So again, this isn't going to be a lot of fun, but I'm going to declare the edges. So I'll just go over here and there we have it. So the way we can interpret this is that the first edge will have an A point of 0 and a B point of 1. So it goes from 0 to 1. And the next edge goes from 1 to 2 and so on, just like I was talking through before. Now remember, these are integers and they are the indexes of existing points. So what we'll do is we've transformed the points, then we access into those transformed points on the basis of these edge indices. So I'll just go right down the bottom and we'll do the drawing. So I want to loop through for each edge. Okay, so I'm telling the engine to draw a line, and I'll do this a whole bunch of times. I want to go from point A. So I access into that array and I say, okay, what is point A for the ith edge? Whatever that is, get its x coordinate, which is the 0th bit of its data. And then we'll do the same thing with the y coordinate. And then we'll do the same thing for edge, for the B point of that edge. And the color will be white, which is just, yeah, maxing out RGB. Okay, so let's give that a go. There we go, beautiful. We've got it in 3D. It doesn't look very 3D right now, but I promise it is. So yeah, it's very fun. I'm very happy with that. So there we have it. Now we have perspective projection. we are turning 3D into 2D and putting on the screen. I don't know about you, always blows me away. So that's it for now. The next video, we will look at transforming this, spinning the cube around and stuff like that. And yeah, anyway, all the best, and I'll see you again soon. Bye.